Let us start electromagnetic waves. Electromagnetic waves or EMW. EMW, electromagnetic waves. So what are we going to study in this chapter, electromagnetic wave? We are going to study the concepts from the previous chapter. Whatever you have studied, that will be applicable, right? And here we are going to discuss about wave. So the concept of wave also will be applicable. So you better also start revising the waves chapter, grade 11 chapter, waves, which was the last chapter in grade 11, and that video also we have uploaded also in our channel. It is there. I will also share the links of those. You can watch that. So let us start. So this chapter will involve all the concept of electricity, magnetism, and also the concept of waves. Okay. So first thing is the background of this chapter. What is the background of this chapter? The background of this chapter was all the previous chapter which you have studied. In the previous chapter, you have studied that so many things, starting from electrostatics. You have studied Coulomb's law, right? So what are the things we have studied? Let us summarize briefly. So a charge whether at rest or in motion produces electric field. Let us call electric field as E vector. So that is the nature of a charge. A charge is a particle which produces electric field when it is rest, or whether it is in motion it will produce. But when it is in motion, it produces magnetic field also. Okay. So suppose if there is a charge particle, it is at rest, so it produces electric field. But if the charge is in motion means I am taking velocity constant velocity, so it produces electric field as well as magnetic field, both. Some sound is coming. Yes, Sam. Oh, link. Fine, I will again send you in your number only. I am sending. I think it is already there. You just check it. Uh, Again, I will share that. Hmm, hmm. 1 minute. I will share the link again. Because it is the same link we are using for the class. Okay. So I have shared the link, Sam. You just check. Uh, yeah, I think they are joined. Some I will add them. Yes. Yes. Now they joined, right? Sam, can you confirm whether they are joined? Hmm. Hari and Manuel, right? Okay, okay, fine. So if they have camera, they can enable it, Otherwise, that's fine. They can see it. Oh, at least audio they can ask questions, right? So if it is possible, audio they can check. Mic. Okay, no problem. Then next class onward they can do that. Fine, fine. Okay, so let us start. So I will just review that we are going to take up this class electromagnetic waves. So first is the background of that. We are seeing about little bit about electricity, little bit about magnetism we should know. Then we will go to this chapter. Okay. So in electrostatics we have seen that if we have a charge at rest, it will only produce electric field. But if there is a charge in motion, that also with constant velocity, then it will produce both electric field and magnetic field. But this electric field and magnetic field will be changing. They will be changing with time, right? Because charge particle is in motion, so this field will not remain same at a given location. You are calculating electric field and magnetic field. But if charge is less, so if you calculate electric field here, this distance is r, and by Coulomb's law, you know k cube by r square you can calculate. But if the charge start moving, r distance will change and field will also change. It will not remain constant, right? Distance will change, so charge is moving, right? So then the electric field is changing and magnetic field will also change. It will produce a magnetic field. That magnetic field is given by Biot-Savart law. So note that this electric field is given by Coulomb's law, Coulomb's law, and magnetic field is given by Biot-Savart law, Biot-Savart law. And because its moving charge behaves like a magnet, so if the charge particle is under motion, suppose a charge particle is under motion, and if it is kept in a magnetic field, external magnetic field, and let us say that there is some electric field also, external electric field, these are external fields, external electric field, external magnetic field. So in the presence of external electric field and external magnetic field, this charge will experience force. Why? Because this charge is like a charge, right? A charge will experience electric force definitely, and it is also going to experience magnetic force because it is like a magnet now. Moving charge is like a magnet. So it will experience both electric force and magnetic force in the presence of electric field and magnetic field, and that force, you know, that is called Lorentz force. That force is equal to electric force plus magnetic force, and electric force is Q E vector, magnetic force is Q V cross B vector. You can take Q common, and this is E vector plus V cross B vector. This is called Lorentz force, right? Lorentz force. Then next is, we have also studied that suppose if you take a current carrying wire and connect with a battery, so you know that there will be electric field lines inside the conductor. This electric field line is given by the battery. The battery supplies constant potential and battery creates a electric field inside the conductor. Note that here the electrons are moving, so there is electric field. Suppose electrons are not moving and it is electrostatic condition, so in a metal there cannot be electric field inside a metal in electrostatic condition. But in electrodynamics condition, when the charges are moving, there can be electric field lines. Okay. Sometimes they will ask question, if there is a current carrying wire, there is also electric field. But we know that electric field cannot be there in a metal. Electric field should be zero in a metal. So we need to clearly answer that electric field is zero only in electrostatic condition when the charges are not moving. But when charges are moving, there will be electric field inside the metal, inside the conductor. Okay. So there is electric field because charges are moving, and you have studied in current electricity that electrons are drifting in this direction with a drift velocity, right? So that means a current carrying wire has electrons moving inside that, right? And there is electric field inside the current carrying wire. So that Biot law also gives us the formula for electric field, right? Electric field due to current carrying wire, you know that. Suppose that is a current carrying wire I. So there is magnetic field lines around it given by right hand thumb rule. Right hand thumb rule, all of you know that. You have to make a thumb like this and make a right hand fingers like this, correct? So this direction, you are curling your fingers in the direction of magnetic field. If you keep your thumb in the direction of current, then your fingers will curl in the direction of magnetic field. That is the right hand thumb rule, right? So the right hand thumb rule, Maxwell's right hand thumb rule, gives us the direction of magnetic field. This is the direction of magnetic field. So this is how magnetic field is going in a circle, and the center of this circle is on the wire, right? This you have studied in magnetism, right? This is what is Biot. So from Biot now let us try to understand very important thing, that current carrying wire means there is electric field. So you can say that this current is producing magnetic field, or you can say that electric field is producing magnetic field. This is the conclusion you have to make. So the electric field in the wire is producing a magnetic field outside the wire. Okay. So this electric field inside this, there is a electric field inside it. Okay. There is a electric field inside that. That electric field is producing this magnetic field outside the wire. But note that this electric field is constant. This electric field is constant. And at a given distance, this magnetic field is also constant, because magnetic field formula, you know, mu naught I by 2 pi r, right? All of you know this formula. So at a distance of r, suppose I am studying at a particular distance from the wire, magnetic field is constant. If you change distance, then only magnetic field changes. So this magnetic field is not changing with time. At a given location, this magnetic field is constant, right? That magnetic field is not changing. So a constant electric field produces a constant magnetic field. That we can say, right? A constant electric field produces constant magnetic field. That we can say. But we cannot say changing electric field produces changing magnetic field, or changing magnetic field produces changing electric field. At least in Biot law, we cannot say that. But when it comes to the Faraday's law of electromagnetic induction, there we can say a changing magnetic field produces electric field. There we can say that. So the next topic which we have studied is EMI, electromagnetic induction. Electromagnetic induction. In this electromagnetic induction, you have studied that a changing electric field, a changing a changing magnetic field give rise to electric field. Electric field means voltage difference, EMF or current. You can write other terms also, EMF or current, right? You have studied this. Suppose there is a coil and there is a magnet passing through the coil. So there is a changing magnetic field line, and that changing magnetic field line creates a change in magnetic flux, and change of magnetic flux produces current or EMF, and because there is a current in the wire, there is an electric field produced, right? You have studied that there is electric, but note very important thing, that this electric field which is produced, this electric field is non-conservative electric field, non-conservative electric field. So the electric field produced by charge and electric field produced by changing magnetic field, they are not the same nature. Their nature is fundamentally different. The electric field lines produced due to a charge is conservative electric field. That means if you move a charge in a circle in a loop, work done is zero. But in a non-conservative electric field produced due to changing magnetic field, if you move a charge in one circle, work done will not be zero. Are you clear that? Yes. These are very fundamental things, right? You should learn all these important things properly, right? When you study NCRT, you don't understand many things there because in NCRT things are not given clearly or explicitly. It is a very condensed version. So you need to properly interpret it without any mistake. That is why when they set question from NCRT, it becomes difficult, particularly conceptual question, assertion region question. Even in JEE Main or NEET, you can see that type of thing. Questions are difficult. This year, questions are quite difficult. Okay, so we have discussed this. Now, what was Faraday was thinking? Sorry, Maxwell was Maxwell Maxwell was thinking. Maxwell was thinking. What he was thinking? Can we produce? Can we produce? Can we produce magnetic field from changing electric field? That was the question. Can we produce magnetic field from changing electric field? That means suppose some coil is there, right? And you change magnetic flux or magnetic field in that. Can we produce magnetic field or not? Because if you can produce magnetic field, then it is just the reverse of this Faraday's law. Faraday's law says that by changing magnetic field, you can produce electric field. He is just thinking the reverse of that, because in the nature reverse thing can happen in nature, right? Nature, anything reverse can happen. If forward can happen, reverse can also happen. Some people think that time can also go back because time is going forward, right? Yesterday, then present, today, and then tomorrow. Some people can think that from tomorrow we can go to today, and from today we can go to yesterday. That is called time travel. That may also happen, right? It looks like fiction, but in nature we do not know, many things can happen. Somebody can go travel in past, present, future, and do so many movies you might see. They may make on this concept. Some Hollywood movies or some movies, in Tamil movies also you might have seen some fiction, science fiction based movies. Time travel, right? So many things are there, but we do not know about that. Okay. So the question was that only, can it reverse or not? Can reverse thing will happen in nature or not? That was the question. It may happen, may not happen. So whatever happen has to be proved by experiments. In science, that is what. If experiment prove, then it happens. And if experiment does not prove, then it does not happen. Or we do not know whether it happened or not, unless it is proven by experiments. So Faraday did experiment and he proved that yes, it is possible that a changing magnetic field, uh, changing changing electric field produces changing magnetic field, and that changing magnetic field and that changing magnetic field in turn in turn produces changing electric field changing electric field which again produces which again give rise to give rise to changing magnetic field and so on and so on, right? So Faraday proved this by experiment, and that was a major breakthrough in research. Okay, Maxwell and Faraday, their research was very ground breaking research. The Maxwell's whole research changed the way of communication, the satellite communication, and radio wave communication, whole communication. Now we can watch television, we can see videos, live streaming, and all this. How it is possible? It is due to that Maxwell's Faradays. They have done a lot of research in this field, right? We do not know in future what will happen. Technology is growing, and quantum mechanics is also coming. So some matter can just travel from one place to another with the speed of light. We do not know, because it can just disappear and it can appear anywhere else. Some technology will be there, some quantum technology. We do not know. This year, last year, I think on quantum entanglement, they got Nobel Prize in physics, right? So things are changing. We do not know in future what will happen. Which looks imaginary can become real also. Okay, right. So changing electric field produces changing magnetic field. So how it is happening? Changing electric field produces changing magnetic field. That is what Maxwell found out. But we know changing magnetic field produces changing electric field. That is Faraday's law of electromagnetic induction. So both are changing, but they are producing each other, and this is what is called electromagnetic waves. Electromagnetic waves is made up of changing electric field and magnetic field. A changing electric field produces changing magnet. Changing means in the sense how it is changing. You can ask how it is changing. It is changing with respect to time. It is just like a this wave function. Oscillation. All of you have studied oscillation. Oscillation means it will go up, come to the mean position, go down, again come back to mean position, again go up, like that. In between to mean position, it will change or it will oscillate. So same manner, the electric field value is changing between a minimum and maximum in a sinusoidal manner. Similarly, the magnetic field value is also changing between minimum and maximum value. So it is oscillating or changing. What is oscillating? It is not a particle which can oscillate. The values oscillate. The value changes, right? The value changes with respect to time. So that oscillating electric field produces oscillating magnetic field, and that oscillating magnetic field again produces oscillating electric field. They keep on producing each other, right? And in that way, energy travels in electromagnetic waves. So that is the topic of this chapter that we will be discussing in that, right? So this was the introduction, and read NCRT. The same introduction will be given, right? And they have also mentioned in Indian scientist, I think Chandrasekhar, who produced the electromagnetic wave in the laboratories, okay, in West Bengal. In India, they were doing also research, and they produce radio waves, radio signals in the laboratories, and they used to send the radio signal over some kilometer. Some kilometer means nearby places they can send that electromagnetic waves. That was the first discovery in India. Okay. Then let us understand how Maxwell proved that. What is the experiment he did? So the experiment which Maxwell performed is this one. In NCRT and many textbooks, things are given complex manner, but let us understand in a simple manner what it is. Okay. So suppose this is a capacitor, and let us say the current is coming here, and this current is changing. How it is changing? Because you may connect it with a battery. Suppose you connect it with a battery, and there is a switch and there is a resistor. This is resistor, this is switch, and this is battery having voltage V. This is a capacitor. So what happens as soon as you switch on? As soon as you switch on, what happens? So you know that this is RC circuit. What this circuit is? It is RC charging circuit. It is a RC charging DC circuit. It is not AC circuit. It is DC circuit. DC circuit. AC circuit you have already studied the last chapter. AC circuit was when you are putting a AC signal, but here we are not putting AC signal, we are putting a DC signal. In battery we are putting and you are switching on. As soon as you switch on, you know charge changes with time, and the way charge changes is Q is equal to CV 1 minus E power minus T by RC. This is the way how charge develops. And time 0 you have switched on. Note that you have switched on at time 0. At time 0 you have switched on. So as soon as you switch on at time 0, the charge starts flowing and charge starts developing here. Initially there was no charge, but at some time there is some plus Q minus Q. So this plus charge will be developing here, minus charge will be developing here, right? On the inner face of the capacitor, charges will develop. Because of these charges, there will be electric field lines will be developed. You know, electric field lines goes from positive to negative. So this electric field line will also develop. This electric field line will develop. So if there is more charge, more electric field line, less charge, less electric field line. So initially there is no charge, so no electric field. As soon as you switch on, charges start developing, so field start building up more and more. So stronger and stronger field will develop. But after very long time, when you take time very large, e per power minus infinity will become 0. So there will be a maximum charge develop. After that, it is fully charged. Once capacitor is fully charged, charge will become constant. There is no further charge development, right? So once charge becomes constant, after that, that is called steady state, right? Steady state means after long time, it is fully charged. After that, charge will not change. Then electric field will be constant. But we are talking about some time before that, right? Before that. So before any time you talk about, here electric field is changing. Electric field is changing inside this capacitor. So note this point, that electric field is changing because charge is changing. And you know what is the formula for electric field inside capacitor? I hope all of you know that. Electric field inside capacitor. Electric field formula is sigma by epsilon naught. Sigma is charge by area of the capacitor. I am writing AC. AC means capacitor area. Okay, epsilon naught. So all of you should know that this is the formula for electric field inside capacitor. AC is the area of the capacitor plate. AC is capacitor plate area. Capacitor plate area. Right? You can clearly see that this electric field value depend on charge. So as charge is increasing, electric field is also increasing. Capacitor area is same, epsilon naught is anyway constant because medium is not there. If you want, you can fill some medium, then epsilon naught will become K times epsilon naught, that you know, right? Dielectric constant, you can fill that. But let us say it is vacuum, charge is just Q, medium is just vacuum. But charge is changing, so field is also changing. So there is a changing field inside this, right? Now what Maxwell did is, Maxwell tried to do some calculation of magnetic field. Maxwell was very much interested in magnetic field. So he taken a magnetic compass, okay? And if magnetic compass shows deflection, that means there is a magnetic field nearby, right? If you take a compass and suppose it is showing deflection, there is magnetic field nearby. So he have taken that magnetic compass and he brought the compass here. And here this magnetic compass or this needle is showing deflection. It shows deflection. Deflection. So it shows deflection means there is magnetic field here, right? We already know that near a current carrying wire there is magnetic field. Suppose this distance is r distance away from this wire. This wire is carrying a current. Of course, this current is also changing. Current is also changing because and what is current formula? You can solve from here current. Current is dq by dt. this differentiation you do. When you do this differentiation, you get V by R e power minus t by R. So this calculation you have already done in RC circuit. So differentiation, when you do, CV comes out 0 differentiation 1 differentiation 0 minus e power minus, that same thing will come, and minus 1 by RC come, minus minus become plus, and this calculation gives V by R e power minus t by RC. So this is the current, but current is also changing with time. Okay. Right. So this current is giving rise to this magnetic field here using Biot law that we know. We already know here the magnetic field formula. What is magnetic field? Mu naught I by 2 pi r. This already we know that. There is nothing new. Near a wire is almost very large wire. Near a very long wire, magnetic field is given by this formula. We already know that. So Maxwell told that what is new? We already know. Faraday already has given. Biot has already given this thing. There is nothing new in that, because wire is carrying current, it produces magnetic field. So he was not surprised that magnetic needle is deflecting. But when he taken magnetic needle inside this, suppose he have taken magnetic needle same distance inside this capacitor. Okay. Same distance means suppose this is the axis of the capacitor, and same distance r inside the capacitor from the axis he is taking the magnetic compass. But there also it is showing deflection. That was the surprise for him, right? How is there is deflection inside the capacitor? Because inside capacitor there is no magnetic field lines. Why? Because there is no current, right? So there is no current inside the capacitor. How can there will be magnetic field? That was his question. Question was, how can there be magnetic field? How can there be magnetic field inside capacitor? How can there be magnetic field inside capacitor? Because there is no, because there is no current, no current carrying wire, no current carrying wire, no current carrying wire. Current carrying wire is not there. How can current means how can magnetic field be produced inside the capacitor? That was the new means discovery. Why? Because according to law, Ampere Circuital Law, let us try to understand Ampere Circuital Law, and this was the inconsistency. This was the inconsistency in Ampere Circuital Law, in Ampere Circuital Law, in Ampere Circuital Law discovered by Maxwell. So Maxwell was the first person to discover the mistake in Ampere Circuital Law, because Ampere Circuital Law says that if there is a current carrying wire, let us say, and if I imagine a circular path here, if I imagine that there is a circular path around it of radius r, there is a circular path of radius r around it, and if I calculate the line integral of B dot dl, that gives mu naught into current inside this loop. So using this Ampere Circuital Law, we calculate this V comes out, and due to symmetry, right, comes out, and integration of this length gives us the circumference 2 pi r, and this is mu naught into current inside I. So that's how, using this Ampere Circuital Law, we calculate the magnetic field around a current carrying wire. So if you use the same logic inside the capacitor, if you use the same Ampere circuital law inside the capacitor only electric field is there, right? Electric field lines are there. There is no current. So if I apply this Ampere circuital law, B dot dl I apply, I will get mu naught into current inside is 0. So this should come 0. Yeah, and if this is coming 0, left hand side will give V into 2 pi r. V into 2 pi r should be 0. That means magnetic field should be 0. This we are applying Ampere circuital law. Ampere circuital law. Ampere circuital law. Ampere circuital law, when you apply inside a capacitor, it says that magnetic field should be 0, but experiment shows that there is deflection. There is magnetic field. From where that magnetic field has come? That was the inconsistency in the, that means somewhere something is this Ampere circuital law, some problem is there. That's what happened in science. So previous scientists, they have done some experiment, they have given some theory, and you have to do a new set of experiments to find out the mistake in that. Right? You have to find the mistake of others. That's what it is, science. Right? What previous people have done, they have done some mistake, you find out what mistake they have done. That is what is research. Research means again search. Keep on searching unless you find some mistakes. And then you write your paper, research paper, you make some different theories. That's what it is, research. Okay. So if you are expert in doing that, then you can go for research. Okay. Okay, so he found out this. Okay, this was the inconsistency. B was coming as 0, but experiment shows that there is magnetic field because magnetic needle was deflected. Okay. Experiment shows experiment shows experiment shows magnetic field inside capacitor which contradicts which contradicts which contradicts Ampere circuital law. Ampere circuital law. So what Maxwell thought that it is not good to say that Ampere circuital law is wrong. Might be Ampere circuital law has done something right. We have to appreciate him. So he was a good person. So Maxwell thought that let us try to modify his theory instead of saying that he is completely wrong. Let us modify his theory and say you are right, but something more you should have done. Okay, so he modifies his theory and he gave the Maxwell Ampere circuital law. So he adds his name also, Maxwell Ampere circuital law. So he says that yes, current is there, but that current we cannot see. Inside capacitor also there is some invisible current. That current we cannot see. Okay, that current name is displacement current. So Maxwell has given another current, displacement current, which is present inside the capacitor, and that current is flowing without any wire. That current is flowing without any wire. So that current is called displacement current. Okay. So Maxwell gave the idea of displacement current to improve Ampere circuital law. Ampere circuital law was improved by Maxwell. Okay. So what he says that there is a current inside that capacitor that is called displacement current ID, and this displacement current is given by the equation epsilon naught d phi E by dt. This phi E is the electric flux. So Maxwell says that there is electric flux is changing, and the rate of change of that electric flux multiplied with epsilon naught gives a kind of current which he is calling as displacement current. So then he says that this displacement current should be also counted in applying Ampere Circuital Law. So B dot dl when we do, and right side when you write mu naught into current inside. In this current inside we have to count two types of current. One is current in the wire which is called conduction current, and another is current due to changing electric field or changing electric flux. Okay. So IC is what? IC is current in the wire, current in the wire, current in the wire, which you can say as dq by dt. dq by dt is the rate at which charges are flowing in the wire or the charges deposited on the wire. That already we have calculated in this case. IC is nothing but dq by dt, which we have calculated as V by R e power minus t by RC in this case. Okay, in this case this current in the uh, is the rate of flow of charge, and that current is, it is in RC circuit only, V by R e power minus t by RC. Okay. So now inside the capacitor there is no wire, so this displacement current is only there. There is no conduction current inside the capacitor. Okay. So inside the capacitor, if you apply inside capacitor, so inside capacitor, inside capacitor IC is 0, but ID is there. ID is not 0. ID will be this formula, epsilon naught d phi E by dt. And outside capacitor, outside capacitor, outside capacitor means what? Outside capacitor means outside wire. We are talking about outside capacitor means what? Outside wire means like this, or you can say near the wire. That will be a better term. Near wire, near the wire. Okay. Near the wire, near the wire. Near the wire we have only conduction current, that is dq by dt, but displacement current is 0. Okay, note that. So if you have to apply inside capacitor, you will take IC 0 and ID you have to apply. If you take outside the wire, that means here near the wire, you have to use this IC equal to dq by dt. ID you have to take 0. So in both cases it will come. Now let us apply this capacitor and try to find out magnetic field. Okay. So suppose this is a capacitor here, and this is the axis of the capacitor, and we want to take any point here at a distance of r. So first of all we have to make a loop like this, circular loop we will make, right? This is the circular loop, and electric field lines we have to also see. So electric field lines will be passing like this through this. So note that we are taking a loop here, which is an imaginary part. There is no wire here. This is a loop, a closed path. Right. So what is this loop area? First of all, let us write loop area. Loop area, let us write as area of the loop. Area of the loop will be taking a circular pi r square, and capacitor area already we have written. Capacitor area. Capacitor area I am taken AC. That can be taken as pi r square. Assume that capacitor is like a circular plate capacitor like this, and this capacitor has radius capital R. Okay. So this is capacitor area, this is loop area. Loop area is the area which you are taking. That loop area may also be equal to capacitor area if you are taking a bigger loop, right? So that area can be also equal. Okay. But note here that whenever they ask you to find electric field, magnetic field inside capacitor, you have to take capacitor area and loop area equal. If they have not mentioned what loop I have to calculate or what distance from inside capacitor we have to take, if nothing is mentioned, you take the loop area same as capacitor area. Okay, if nothing is mentioned. But sometime in the question they will mention that inside at a distance of 2 centimeter, 2 millimeter, that loop you take. So in that case, R we have to take use small r here. Okay, right. So then let us try to calculate what is d phi e by dt. So what is displacement current will calculate d phi e epsilon naught d phi e by dt. So epsilon naught phi e means electric field into area of the loop. Remember here we are taking loop area. Loop area we are taking. Loop area is constant take out. So you will take out epsilon naught loop area into dE by dt. So what is displacement current is epsilon naught loop area, and electric field already we have written charge by epsilon naught into area of capacitor, right? This by differentiation we are doing. So now here you will take this out. So epsilon naught area of the loop by area of the capacitor into dq by dt. Okay. Now this is a very important result. So displacement current can be taken as epsilon naught. I think epsilon naught also will get cancelled here. This will get cancelled, right? Okay, that epsilon naught has got cancelled now. So this got cancelled. So area of loop by area of capacitor into dq by dt. Can we write dq by dt as conduction current? We can write it because dq by dt is like a conduction current, right? We can write it dq by dt. I am writing it like that. Okay. So IC is nothing but conduction current and ID is displacement current. That is the result we are getting. But anyway, IC we know in RC circuit we have already calculated this dq by dt, which is V by R e power minus t by RC. Remember this. This already we have calculated. Right. So this is displacement current and this. Now let us calculate the magnetic field. So magnetic field at a distance r, applying that Ampere Circuital Law, B dot dl mu naught into current inside, but current inside we are writing as IC plus IT, but inside capacitor IC is 0, so we have only displacement current. Okay. Now if I take this displacement current, then I will write this as mu naught into IT, right? And then I will write this ID as area of loop by area of capacitor into IC. Now I will substitute here as B into 2 pi r. So B will become mu naught by 2 pi r area of loop, area of capacitor into IC. IC you can substitute here. So mu naught by 2 pi r area of loop by area of capacitor into V by R e power minus t by RC. This is the full formula for magnetic field inside the capacitor at a distance of r. Okay, clear? Did you understand this? This formula is not given in NCERT. But why should we remember this formula? Because quickly you will solve problem. You want to solve problem within few seconds, right? You have to remember this. Mu naught by 2 pi r area of loop by area of capacitor into V by R e power minus t by RC. And if they have not mentioned where we have to find magnetic field, then in that case take area of loop and capacitor same. So note that if not mentioned what is R, If not mentioned what is R, then take area of loop equal to area of capacitor. If you take this equal, it will get cancelled. Then in that case, this formula will be mu naught by 2 pi r. Right, this will get cancelled. It is like IC only, which you can substitute mu naught by 2 pi r v by r e power minus t by r. So that's the full formula. If nothing is mentioned, or if they are mentioning outside the capacitor, or distance is very large, right? For example, suppose this is the capacitor and they are asking here, anywhere outside capacitor. If they are asking outside, because this is the region of the capacitor inside this. If they are asking inside, then we can use that small r. But if they are asking outside, then we can simply take this. Outside means outside capacitor. Means radially outside capacitor. Okay, note that radially outside capacitor. Radially outside means this R is, note that this, if nothing is mentioned, means what is R? You can take R greater than capital R, or even equal to capital R. So this formula will be equal for R greater than equal to capital R. Okay, that means point is outside capacitor, outside the region of capacitor. If it is within the region of capacitor, it means R less than capital R, you use this formula. But if R is greater than capital R or equal to capital R, you use this formula. Because this loop area and this area, capacitor area, become equal for this. Clear? Yes. All of you have understood this. Anyone, any doubt? Okay, so I think we can wind up till here. Now, in your old NCRT, there are many exercise, means one or two exercise questions are there, which is not there in new NCRT. In our app, you can please download our app if you have not downloaded. I will add all of you uh, today in the, I think some of you are already there in the app. Lalit and others, those who are not in the app, please message me. I will add you in the app, or otherwise you download this EduMind app. Okay, in Google Play Store, you go to EduMind app and download if you have not downloaded. Install that app. So I will add you in also in the group, and we'll send you regular updates, and some tests also I will be creating. So test also link I will share. You can write the test. Okay, fine.